Super. All right. So thank you, everyone. Thank you for being here on our Friday noon talk. Today, we have the pleasure of welcoming Dr. Alex Grimwood. He's a medical physicist at the HCA London Radiotherapy Centre, UK. He has a PhD in optical and ultrasound imaging, and then worked as a postdoctoral researcher investigating ultrasound guidance and developing deep learning tools to automate image guidance and interventions, including radiotherapy. After 5 years in research, he moved into the clinic, working in the team that established London's only proton therapy clinic before joining the HCA 2 years later. And today he'll be talking to us about applications of AI in radiotherapy. So please, Dr. Grimwood, go right ahead.
Thank you very much. That was a great introduction. Thank you. So the presentation I'm giving is titled Current and Future Applications of AI in Radiotherapy. To start with, I'm just going to caveat that this is going to be quite a broad presentation, a rather gentle one, not particularly technical. The reason being that the subject matter, AI and deep learning effectively, is based upon my postdoctoral work, which is out of date, shall we say, by a couple of years, because I've been in the clinic and sort of distanced away from research. But I agreed to give this talk because it's still a fundamental part of what we do and will increasingly be the case as time moves on. So we can already see every year how the technology is rapidly improving, and it's just a matter of time before we have to accommodate it in the clinic. Whilst I was working with Ali in the Proton Beam Therapy Centre, I had the good fortune to receive a Topol Fellowship specifically within the NHS, funding from the NHS geared towards trying to implement AI within the clinic. And it's been a challenge. So I'll talk about that in future, potentially towards the end of this presentation. But the long and short of it is that at the moment, the kind of initiatives that are available to us as clinical physicists can be almost, terminally inhibitive to actually getting the tech in to where it is needed. So with that in mind, let's take a step back and have a look at the presentation, what we're going to actually cover through most of it. So a quick overview. I want to go back to basics for people in the audience who may have heard of AI as a self-contained term without necessarily having a grasp of some of the fundamentals. So I'm going to go through some published examples of AI, specifically focusing on deep learning in radiotherapy and medical physics, and use them as a basis to describe what the technology actually comprises. And I'll slowly increase the level of complexity and become more general in my descriptions of them. That will be really the bulk of this presentation, but I will finish with discussing the push towards a generalized approach to AI. So these are AI models that you typically see in the media, and you see the likes of Google promoting, which are meant to be the toolkit, the Swiss Army knife of AI. So things like, ChatGPT making your lunch. That doesn't quite exist yet, but is certainly where the smart people are trying to head. And finally, I've got one last slide just discussing my experience with AI, really trying to implement it in the clinic rather than in research, and the kinds of challenges that are currently being experienced by people like me. So we're going to start off with classification and the artificial neural network. So this is the absolute bare bones of what makes AI. It's a neural network. And this image you can see is a single node in what would be a broader network. What I have here is a list of some of the key terms and concepts that go along with this. And down at the bottom of most of the slides, including this one, you'll find links. So if I share this presentation, you'll be able to check out where the source data is and have a look at some examples. If you're interested and want to follow up in your own time. So typically, a neural network consists of multiple nodes, such as the one you see here. It requires an input, which is typically a piece of data, such as a word or an image, or any kind of structured data that can be fed into the node. The input will be weighted and will have a bias applied to it. So these are effectively parameters or terms in a very simple mathematical function. So you can think about it as weight being the gradient, for example, in the curve, and the b being the intersection of the curve with the axis. This will be used to put into a function to have some output z of the node, at which point that output is then fed through to something called an activation function, which is an ancillary function. It's effectively treated as a threshold trigger. So if your output from z reaches a certain level, it will be typically either filtered out because the signal wasn't quite high enough, or allowed to pass on through by the activation function. So that's a slight simplification. There are variations on it, but the idea is that when you have many of these nodes in your neural network, you really don't want them all firing. You want to have a more refined process of regulating what signals come out of neurons as they're being trained, and the activation function allows you to do that in such a way where the whole training process doesn't run away. So finally, from the node, you reach an output, which here is y hat, and is generally termed as a prediction. And this prediction is then compared with a predefined label, which is typically applied by the user as part of the training. So I've waffled on a little bit here. Let's see if we can break this down a bit. So input, label, and output are all typically images or text prompts, the things that are effectively made by us or collected by us and then fed into the network. And then we look to compare the output with these things. So a node is the integral part of the neural network. So it's the node in the network. And there are typically many nodes in a layer. And what we do is we stack these layers on top of each other, and that's where we get the term deep learning from. Deep learning is a colloquialism that signifies that the network we have is many layered, so it's very deep. We have weights and biases, and these are our trainable parameters. So these are the elements of the functions at our node that we adjust, and that's the process of training. And we adjust those to optimize the output so that it agrees with the predictions that we make, agree with our labels. We have an activation function, which, as I've said, is really there to regularize our node output and to stop runaway processes occurring as we go through our training process. We have a loss function. So I haven't discussed this yet, but the loss function is, you can see an example in the top right-hand corner of the image. It's typically a very simple function that allows us to, well, the loss function itself is the loss of the error that we calculate as part of our loss function is typically very simple. It allows us to compare our predictions with our label. The loss function is an optimization space where we can minimize the loss. So we can minimize the error between our prediction and our label. And we use this loss function to backpropagate, to train our nodes by minimizing the predictions and labels. We do this by incrementally, typically with something like gradient descent, incrementally updating the parameters at our nodes, our weights and biases, ever so slightly using partial differentiation and trying to trace back what a slight shift in our loss would look like if we applied the terms to our weights and losses, weights and biases. So the absolute most standard example that we typically see in medical physics is a convolutional neural network. And a convolutional neural network is characterized by the functions being performed at our nodes emulate a convolution kernel on an image. So we'll take like a 3x3 window, which will be a convolution filter, and we'll apply that to an image. And we'll do that using our neural network. And as it's a deep neural network, each layer in our neural network will contain a series of convolution kernels that are all slightly different to each other, and we'll stack those on top of each other until what comes out at the other end will be, in this case, in the simple classification case, a unitary output, i.e. a number that will signify a category. So when you're going onto Google to learn about these things, or Kaggle, which is a great resource, the first thing that you'll typically see is cats versus dogs. The reason being that training data is hugely abundant for cats and dogs. People love them, and it's easy to access on the internet. So this is where a lot of the initial training data came from. And your input is a 2D image. Your output is, as I said, a classification, which is typically an integer of some description to signify whether an image has been labeled as a cat or a dog. And your layers are 2D convolutions. And the training labels are human applied. So that's something that's fed into the network during training. And the loss function is a gradient descent. So you optimize the network by showing it images, telling it what the answer is, and getting it to learn before then showing it an image and seeing how well it guesses or predicts for itself. So what does a clinical example look like? So this is probably the only bit of my research that I'm going to quote in this paper. This is a MICI paper from 2021, if I remember correctly. So what happens here is that I have a volumetric ultrasound scan of a prostate patient, and this is done using an electroclarity system. We trained radiographers to set up the patient using the electroclarity, but what we found was that they had more trouble setting up the ultrasound probe to adequately visualize the prostate on the patient than they did actually setting the patient up. So I came up with a tool that would classify images within the ultrasound scan display, so they could automatically be labeled to advise the radiographer on whether they needed to move the ultrasound probe a little bit left or right. So what you can see in the first image on the left-hand side is a probe that's pointing away from the prostate. The prostate's not visible. Can't really see anything, maybe a bit of shadow from the pelvic symphysis. In the central image, you can see the prostate is visible. It's marked by PR, and you can see the seminal vesicles marked by SV, but you don't see the sort of central anatomical features as you do in the right-hand side image. So in the right-hand side image, you can see the penile bulb, which is a great indicator that you're pointing the probe in the right place. You can see the prostate. You can see a little bit of shadowing from the pelvis and the bladder behind that. So I trained a CNN to classify these images, and it performed a separate task, which was to recommend whether or not the probe needed to be adjusted. So this is where we start to see a concept that we'll talk about more in future in this presentation, which is the idea that you have multiple tasks. So something like a classifier is regarded as a highly specialized tool. It really can only do one thing, but already at this stage of simplicity, you can already explore how to multitask with these simple tools. So the idea is the multitask is relatively constrained. It's just identifying where the probe is positioned, but it's also recommending an adjustment. Yeah, so I'm going to leave that because I think the other stuff I have discussed in the previous slide. So moving on to the next level of complexity, we can think about segmentation and convolutional neural network. So here we have a quick schematic of a slightly more complex neural net, but this is, again, an absolute classic that is still used widely, and I think in off-the-shelf AI tools in clinic. So we are going to apply our convolutions in our neural network, but instead of reducing down to an output that's categorical, what we're going to do is try and remap our neural network output back onto a 2D matrix, a 2D space, with the same dimensions as our input image. And this is why you get the term neural network, because what you do on the left-hand side of the U is you encode the image data down into a very deep, but very narrow neural network. So it's a neural network that has a lot of parameters, but might not have much in terms of 2D space. So once you've done that, you're effectively extracting features or encoding abstract information from the image. You then want to apply that spatially distributed onto the image. So what you do is you then upsample and re-encode that data on the right-hand side of your neural network. So what you're doing is creating a shallower and shallower network with a broader 2D face, effectively. And this allows you to map out your categorizations onto the 2D image matrix. So why would we do this? So the reason we do this is because you're able to extract features at different scales in the image at each layer as you go down the U-net. So this means you can identify broad spatial features and fine spatial features. So effectively, you have convolutions at different scales that are all being encoded. And in order to preserve those features at different scales, you have something called a copy and crop, so crossover linkage in the neural network at these different scales. So why would we want to do this? Well, obviously, we want to find out where our cats are in an image. So you would train your neural network by showing it loads of images of cats and telling it that the output should be a segmentation mask of a cat. Obviously, not particularly useful as an example on its own. But if we start looking at the example here that was published by Dong et al. In 2019, you can then apply a multi-organ segmentation and begin to automate your organ at risk segmentation, for example, in this case, in thorax CT images. So here now, your inputs, instead of being cat pictures, are going to be planning CTs, and your outputs are going to be segmentations of organs at risk, which you've, again, manually labeled yourself. But we're going to introduce something slightly more interesting this time, which is something called a GAN. So in this particular case, Dong has added something to our basic run-of-the-mill U-net. He's added something called a generative adversarial network. Why would he do this, and what is it? So a generative adversarial network is a new, or something I haven't spoken about before, neural net that is able to take some data, it could be random noise or it could be an image, and generate a synthetic best guess image. So this generator will effectively churn out synthetic images to its heart's content after it's been trained. Why would you want to do this? You want to do this because clinical data sets tend to be quite small. And one of the key stumbling blocks with deep learning and AI is that you need very large data sets in order to sufficiently train your models. So this has always been a key limitation. And the more complex your network gets, as you can see, U-net is slightly more complex than a classification model, the more data you need to train. So this is related to the fact that the more complex your model is, the more trainable parameters you have, And then the more iterations of training you need to go through, the greater the diversity in your training set you require to make sure all of those parameters are optimally trained. So effectively, they've been shown the whole of their training parameter space, which the more parameters you have, the much larger that becomes. So with that digression, what Dong is doing is he's using a GAN to generate synthetic training data that he can then show to his UNet. And that synthetic training data is itself derived from the limited training data he has. So he's using his training data in two ways. He's using it to train his GAN, and he's then also using his GAN conditioned network to help train his UNet. So let's talk a little bit more about generative adversarial networks. I had to include this because this is from Google's own website, and I think it's hilarious that you need a discriminator to tell the difference between the fake $10 bill and the real $100 bill. But, you know, here we are. So if it's good enough for Google, it's good enough for us. But this is a classic GAN example. It really breaks it down into the key structural element that makes a GAN, which is that there's a generator and a discriminator. So what you have here is a human-made set of generated data, which are these badly drawn dollar bills. You have a GAN discriminator. So the GAN takes on the task of trying to discriminate fake from real. And as you can see, if you look down towards the bottom of the page, the more you train your GAN, the better its discriminatory power becomes. So at some point, you have to use a well-trained discriminator to challenge, to be an adversary to your generator. So GANs are particularly useful when you need to generate synthetic data, or when you need to discriminate against very close approximations. Now, in medical physics, not quite there yet. So before I go on to the next slide, in medical physics, we tend to want to use the generator element of a GAN. So discrimination is important, but the point of our adversarial network is usually to create synthetic data. So that means that we'll use our GAN to try and create synthetic images. So discriminator is important. You need both the generator and the discriminator, but in terms of application, we're really only interested in one of those two things. So the best example I have for this is the cycle GAN, and this is something that I did use in a research project, and although I don't have a reference for it here because it's not a radiotherapy project, it's something that you would do find in radiotherapy, as I'll discuss in the next slide. But to give you an indication of what the cycle GAN does. So a cycle GAN is able to take an image and to synthesize that image to create a different image, which is an approximation or a change in features in the image. So this is the classic example of a cycle GAN that can turn images of zebras into images of horses, and vice versa, horses into zebras. And why would we want to do both? So we want to do both because it requires something in the training called a cycle consistency loss. So it basically looks at a way of trying to use the comparison of both the zebra and the horse to consolidate the training of the model. So here on the right-hand side, we see one half of the training process where the cycle consistency loss is being minimized by looking at minimizing the difference between a fake and real zebra. But if we do that for both the horse and the zebra, your cycle consistency loss has to be much more effective. So it's much more robust, which makes overall your entire GAN components, the generators and the discriminators for both horses and zebras, much more effective. So if we do this, what we can then do is use something like a cycle GAN to create effective simulations of, say, one imaging modality. So a great example that has generated a lot of publications and a lot of interest in the research community is trying to generate synthetic simulation CTs from MR images. So you will train a cycle GAN to create synthetic CTs from MR. That cycle GAN will also create synthetic MRs from CT. But the synergism of doing both tasks at the same time will improve the robustness of what you want at the end, which is a generator that can generate good synthetic CTs for simulation from your MR scan. So this is what Kang et al. Have done. They've managed to do a lot of image pre-processing to try and approximate the registration, so the position of their CT and MR data. So there's effectively less work for the cycle GAN to do because all organs, all bones, all anatomical elements in both images are effectively in the same place. But they will then selectively take the generator, the synthetic CT generator, and put that into their TPS and see how it compares to their original CT simulation. So why would you want to do that? So intuitively, I've sort of just said off the top of my head that, obviously, this is something that generates interest, but we're increasingly moving towards online adaptive radiotherapy, at least in aspiration, if not in the clinic. And with MR-Linacs, with Halcyon and other technologies, people are definitely much more keen about looking at things like online adaptive. So how can you actually generate a plan from a scan with the patient actually lying on the treatment couch on that day? So this is where it comes into its own. And how are we doing? So the results are good, but they aren't perfect. So I'm not going to tell you how wonderful Kang's model is, even though if you go and read the paper, you'll see that it is good. And generally, the results are impressive. His gamma scores are great. In terms of spatial approximation, your ability to distinguish between a synthetic and a real CT the results are great. But for specific structures, in this case pelvis, you have quite large mean absolute errors, so it's not perfect. Some of the reasons for that are because he didn't have access to large enough training data sets. Also because what you tend to find is things like contrast agents, which may show up as bright spots where you'd expect dark spots, can confound the cycle GAN. So it interferes with its mapping. And there may also be a lack of diversity. So, a lot of abdominal scans effectively might not be challenging the network enough to make it robust to its test data, to the actual data outside of training. And additionally, there might be a problem with data conditioning as well. So deformable image registration, image pre-processing, these elements might not be adequate. So focusing on the data limitations, one of the things that makes off-the-shelf models from big companies such as Google and OpenAI so potent is the fact that they have access to very large data. Training data sets. And this is really one of the keys to the state-of-the-art models that we'll see. So here I've got a screenshot, again, perhaps more interesting than seeing a dachshund in a swimming pool than it is seeing a pelvis CT. But this is a completely synthetic frame from a 4K movie generated by Google VO2. If you go to their website, you can see many more examples. It's quite impressive what they're actually capable of doing. And it won't be long before these companies get their hands on enough medical data to create models that are much more useful to the clinic. One example that's getting a lot of attention recently is Google MedPalm, which is an LLM, so a chatbot, a bit like GPT that's able to synthesize reports and work effectively as a clinical chatbot. So these models incorporate generative concepts. They incorporate some other concepts that we haven't talked about that are effectively still based on the idea of encoding or embedding network sort of features, deep learning features from your input. They also use self-attention, which is something that I haven't gone over, but it's the next step along where your contextual sampling is not just spatial, but is also in some shape or form temporal. So you're looking at different frames adjacent to the one in the CT that you're interested in, for example, or you're looking at words adjacent to or sentences adjacent to the words that you're particularly interested in your large language model, or you're looking at adjacent frames in a movie when you're doing processing on a specific frame in a movie. So where is this all heading? This is basically moving towards what people are trying to sell you with the current state-of-the-art LLMs, which is a generalized artificial intelligence. So truly generalizable AI will effectively be able to perform a whole range of tasks flexibly and reliably without requiring any further conditioning or training. So we don't have that yet. What we tend to do at the moment, even with state-of-the-art LLMs, is we tend to have something that's relatively flexible, but then it will be applied, conditioned, and trained to do a specific task. So eventually, these generalized AIs will become more common, but for the time being, they're relatively task constrained. However, even now, they're still able to do things like answer patient queries with apparently better bedside manner than most clinicians. That's according to Yelaman Chile from 2024. You are able to repurpose LLMs, chatbots, to do volume contouring, and they are also supposedly capable of synthesizing medical reports in a convincing manner, according to Meng from 2024 again. So we're being sold the idea that you can have one model that can perform multiple tasks. And we're being sold almost the illusion that this is easy for them to do. But these models are only able to achieve what they've done based on incredibly large data sets, which we still do not really have in the clinic yet. The availability of such large data sets as the ones that you see out on the street are non-existent. They're just not there yet. There's also still an issue of inconsistent performance. So if ChatGPT gives you a spurious answer to a question, it's not a problem, but in clinic, obviously, it's a big issue. And it's also an indication that the models that we're using are not yet truly generalized. They're still really dedicated towards filling very niche, very specific tasks. Another thing that will be a limitation is that at some point text prompts are not going to be enough. So at the moment, you might see colleagues next to you with ChatGPT open on their screens, and they'll be typing away, asking questions that perhaps they shouldn't do based on the latest task group report or AAPM guidance. Eventually, you're going to need a much more refined UI if you want your model to be truly general. You're going to need it to interact with you in different ways and to be more flexible than sitting at your desk typing at a keyboard. And finally, you're not going to be able to employ an AI, even an LLM today, without further regulatory guidance or better working practices. So we still need to understand how best practice should reflect accommodating deep learning technologies. So as you can see, we're already having these debates about very specific tasks such as segmentation, so very specialized AI models. At least over here in the UK, it's still very difficult to try and establish QA routines, for example, for deep learning. It's still very difficult to try and establish consensus around the best way of measuring performance and assessing whether or not these technologies will still be working 10 to 15 years from now, when the data that's being fed into them, either people's anatomies or the technologies we're using for our CT scanning, has moved on. So why should we do all of this? Well, the benefits are potentially quite profound. If you have one generalized model that's able to perform multiple tasks, you're potentially going to see substantial benefits in efficiency through having a persistent assistant who's always there to help you with the mundane tasks. So you can think of a medical physics clinic where you never have to touch an Excel spreadsheet again, or where you never have to fill in data into QA track because someone's already doing the data collection for all the QC tests that have been automated already by, you know, your generalized model. The limitations are that it's still effectively a product, it's a tool, and therefore will require extensive QA. So it's easy to QA something that is a single purpose instrument. How do you QA something when it performs multiple tasks in a way that's not always superficially clear or understandable? Increasingly, because of these more complex behaviors, regulation and governance is lagging behind where we are. So as I said, we can see that even now with auto contouring tools. What's it going to be like when we have LLMs that can actually do the auto contouring, write the reports, and speak to the patients? And almost the most important issue is what happens when an error is made, because liability is obviously much clearer when there's a person wielding a tool, but when the tool is so ingrained into the working environment, when do we blame the tool and when do we blame the user? So I guess the obvious analogy of this is with a self-driving car. If it runs a person over, you know, who do you blame? Do you blame the car? Do you blame the company? Do you blame, you know, at what point in the chain is there a liability to be answered? So that's a bit of, like I said, a bit of a broad brushstrokes run through AI practices. How does it relate to my personal experience? So I started off in research, and over at University College London, at the scientific computing department, and in a research institute dedicated to the computing and medical imaging. And there were a huge number of opportunities. There's so much research interest, and the field is moving at such a pace that it's very exciting, and there's a whole lot going on. So there are countless opportunities where it's possible to apply AI to clinical issues, clinical problems in radiotherapy. However, in terms of actually getting to the application stage out of the research stage, things are much more difficult. A lot of this is down to that sort of brick wall, shall we say, between the laboratory and the clinic, so effectively between research institutions and the NHS itself. And these are totally understandable. So in the NHS, there is the political will to see more implementation of AI and to see more innovation around AI and technology in general. However, because the field moves so fast, at the senior level especially, there is potentially a lack of not just technical understanding, but of the implications of trying to push through the development at a clinical level. What does it actually take to do the R&D? Additionally, because the NHS is a public sector service in a country where funding is constrained, there is a lot of lip service. And as I said before, I was lucky enough to receive a fellowship myself to fund research applications. But the funding was just enough to cover my salary for, I think, something like 25 days throughout the year. So if you tried to fit a research project where you're going to implement a new AI technology in clinic, you cannot, as one person, do that in the space of 25 working days in a 1-year period. It's impossible. So there is there is lip service, but there's not necessarily a joined up initiative strategically focusing on key tasks and then funding them adequately. In addition to that, obviously, it's something that I'm interested in, so I'm going to put in spare time. I'm going to make sure that, you know, we could, at least in my department, try and work towards it. We then came up against issues with governance and outsourced IT. So in this case, it's a risk aversion problem. We would regularly face the issue of trying to convince outside stakeholders that what we were doing was beneficial and worth the risk. And to them, due to the question of liability, that was a losing argument. It's always very tough to make that argument. So typically, the time that I did have dedicated to trying to implement the technology was not used on developing the technology. It was used on trying to convince people through risk assessments or paper trails that there were processes in place to allow safe use of the technology, even though it didn't already exist. And finally, public perception was an issue. So I've been on a number of listening exercises with NHS service users, patients, and listened to their concerns and their reticence around sharing data or training these models that are incredibly data hungry. And frankly, there is a lack of institutional trust, which means that there is no yet clear solution to providing the super huge data sets that are still required to train these models within the NHS framework as it stands. So, and that goes for the clinic as well as the laboratory as well. It's getting better, and the NHS may have some solutions in the pipeline, but technology in medical physics, in radiotherapy development, technological development is constrained really by data, not by access to new and novel techniques. But yeah, on that sunny note, I think I'll end it there. I know it's only 45 minutes and it's a bit of a whistle-stop tour, but I hope there's a little something in there for you all. So thank you very much.
All right, thank you so much, Alex. We have time for questions. You gave a very nice primer on AI and imaging and medical physics, which I appreciated. I'm sure we have some questions though from our audience. As always, please, if you're on Zoom, you want to ask a question, either unmute and ask it yourself, or if you type it into the chat, I will read it out loud. Anyone in the room?
Well, everyone's flagging.
You very briefly talked about your own work. Maybe I'm curious what you're working on. What's your current research right now that you're looking at?
So yeah, the reason why I've talked about my own work is because I've parked the fellowship after moving into the my new post in the private sector. So at the moment, I've been in post for just over a year. I haven't performed any research in that time. I am very interested in a MICI pool that has just gone out, Grand Challenge. I don't know if you've heard of MICI, but it's an medical imaging, computing, and AI conference. They've just released a grand challenge looking at trying to come up with the best techniques for generating synthetic CT from cone beam CT and MR data sets. It's a brilliant opportunity because they're providing training and test data and then validating everyone's models. So anyone that basically wants to compete can compete. So I might use that as a way of insinuating myself back into the work that my Topol Fellowship started. And we'll go from there. That was based around proton therapy, where I think dosimetric evaluations of patient changes on set are much more critical. So looking at ways to convert cone beam to CT data is much more vital, because then you can do your recalculation, plan recalculation, etc. But yeah, that's something that I've got to kind of insinuate into my working day without making my boss too angry.
Thanks. Sharon, you have a question.
Yes, thank you so much for the presentation. I have a question about your new role. You know, you've gone from academia or from a clinical setting to a company where access to data is even more restricted.
Yeah.
So for you to, I don't know your new role, but to generate any type of models that would be generalizable or used by a commercial entity in the clinics, where will you get the data? Or how do you access that data?
Yeah, this is absolutely a brilliant question. So just briefly to contextualize where I am and how far removed it is from research at the moment. So I started off, my last postdoc position, let's say, was at UCL. From there, I moved into the clinic at the Proton Beam Therapy Center, which was a good move because there's still room for development with protons in the UK. And then my research fellowship basically came along looking at trying to implement deep learning in the clinic. After 2 years of working there, I've now moved to a small 2-LINAC private center where research R&D is really not the priority. So there will be no access to training data or any substantive medical data sets through my day-to-day work in a 2-LINAC center. It's not possible. There is still some R&D activity going on at the Proton Therapy Center. They are developing very good links with UCL and with Mathrad, who you might be able to see here on the screen. That's a direct link with UCLH, where the Proton Therapy Center is. So there are ongoing efforts, I think, if I could put it diplomatically, to get that kind of data. There are also the initiatives such as the one I was just talking about under MICI, and international competitions and data sets are generally becoming incrementally more available through those processes. So,
but then all that data is very, every single group is using the same data. So again, the generalizability is questionable, and even if you have,
it is questionable. Yeah, I agree. And I think this is one of the situations where, as loath as I am to say it, coming from a public sector background, I think private sector companies that provide these models are in potentially a better position. So if you've got a company, for example, let's say like Envision or one of the vendors, they can reach potential agreements where they can hoover up data in the name of quality assurance, ongoing quality assurance of their models, potentially from client sites, if that can be anonymized properly, where they can keep their models up to scratch, but they can also build up larger and larger data sets. And it wouldn't surprise me if companies such as Electa and other entities are actually in the process of doing that.
Thank you.
That insight. Any other questions for Dr. Grimwood? If not, I'd like to thank you once again for speaking to us today, and thank you all for being here today. Have a good rest of your Friday and a good weekend. Thank you.
Thank you very much.
And you mentioned, oh, you're still there. If you have your slides,
I'm still there.
if you email the slides to either myself or Ali, we can make it available to our unit.
Okay, happy to do that. Thank you again, Peter. Thank you very much.
Thanks a lot. Bye bye.